Good day, everybody. How are you all? Today we are going to talk about sampling distribution. So here I go. We are going to talk about sampling distribution and the central limit theorem today. So we will construct the sampling distribution of a sample mean. Sampling distribution means probability distribution of the sample mean. So you will have sample mean values on the horizontal axis. On the vertical axis, you will have relative frequency or probability values. So the probability density curve with the sample mean on the horizontal axis, which is also a bell-shaped curve, is called the sampling distribution. And then we will use the central limit theorem. Construct the sampling distribution of a sample mean. So as you can see, the big rectangle is the population. From this, we are drawing several samples, which are shown in each of these ovals. Each of the sample will have different sample means. Why? Because each of the sample is totally different, so they will have a sample mean. So you have so many values of the sample mean. Now you can divide all the sample means into different groups. So suppose there are 50 sample means. We can, for example, divide these 50 sample means into 5 or 6 groups on the horizontal axis. So you have the lowest value, then we will select a class width, and that the first class, and on top of that first class, which is the lowest value plus the class width, a class interval, we will draw a vertical rectangle. The height of the vertical rectangle is the relative frequency or the proportion of out of all 50 sample means, because there are 50 samples, how much falls in the first group. The height of the first rectangle is the relative frequency of all the sample means in the first group. If several samples are drawn from a population, they're likely to have different values for X bar because the value of X bar varies each time a sample is drawn. X bar is a random variable. For each value of the random variable X bar, we can compute a probability. The probability distribution of X bar is called a sampling distribution of X bar. So probability or relative frequency on the vertical axis and X bar on the horizontal axis divided into groups. On top of each group, a vertical rectangle. Height of the rectangle indicates the relative frequency in each group. Join the top roofs of these vertical rectangles, so you get a bell-shaped curve. And then they explain this by a tetrahedral die. I will not go into this. So basically, you are throwing the tetrahedral die 3 times, and all these combinations are possible. As you can notice, one is the mean of the first sample, which is 111, means the tetrahedral die, because it is thrown 3 times. Each time it shows number 1 on the top. And so it is 111. 3 times, 3 ones, average is 1. Because 1 plus 1 plus 1 is 3, divided by 3 is 1. So there are so many means, so many means. But the interesting thing, if you find out the mean of all these X bars, the mean of all the X bars, that is, put the value of all the X bar, which are in bold letters, bold numbers, okay? Put all of them in L1 of the calculator, calculate the sample mean of this sample means, or it will come out as the population mean, which is 2.5. Earlier, they showed that the population, that is 1, 2, 3, and 4, 4 numbers, their mean is 2.5. So what the next slide is showing, telling us that the mean of all the means is also 2.5. Notice the standard deviation of the population is 1.118. So you add all the 50 values of X bar. How many values? I don't know, more than 50, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 64 samples. So you have 64 values of How did I get 16 times 4 is 64? 64 values of X bar, put them in L1, calculate the mean of all the 64 X bar. You'll still get it as 2.5, which is same as the mean of the population. But the standard deviation is different from the standard deviation of the population, which is 1.118. So although the mean of the sample means is equal to mean of the population, the standard deviation of all the sample means is different from the standard deviation of the population. So what is the relationship between the mean of the sample means and the mean of the population? Mean of the sample means is mu x bar is equal to mu. So that is the mean of the sampling distribution because you have the sample means on the horizontal axis, probability on the vertical axis, the center where the peak is the highest, the center value at the bottom, in the bottom axis, horizontal axis is still equal to the mean of the population, which is mu. Mu x bar is the mean of the sampling distribution. That is equal to the mean of the population. As we noted, the standard deviation of the sampling distribution is different from standard deviation of the population. Sigma x bar is 0.645. Compare that with the standard deviation of the population is 1.118. So the question is, what is the connection between 1.118 and 0.6455? And that is 0.6455 is 1.118, which is sigma of the population divided by square root of the sample size. Here the sample size is 3 because we are tossing the die 3 times. So if you do sigma divided by square root of 3, you will get sigma x bar. Hence the relationship between sigma x bar is the standard deviation of the spread of the sampling distribution that is equal to population standard deviation divided by standard deviation divided by square root of the sample size. Okay. Among the students at a certain college, the mean number of hours television watched per week is mu is 10.5 and the standard deviation sigma is 3.6. A simple random sample of size 16 students is chosen from a study of for a study of viewing habits. Let X bar be the mean number of hours of TV watched by the sample students. Find mu X bar and the standard deviation sigma X bar of X bar. So we know mu X bar has to be equal to the mu of the population, which is 10.5. However, the standard deviation of the sampling distribution, or sigma X bar, will be sigma, which is 3.6, divided by square root of the sample size, which is 16. So 3.6 divided by square root of 16 is 4. 3.6 divided by 4 is 0.9. Notice the population, the standard deviation is 4 times the standard deviation of the sampling distribution. That is, sigma is much greater than sigma x bar. And there is some sample problems here. So basically here they're calculating a probability distribution. Okay. So probably consider again the tetrahedral diagram. The sampling distribution for x bar can be determined from the table of all possible values of x bar. The probability that sample mean is 1 out of 64. Why? Because 1 appears only once out of 64. Okay. Probability of 1.33, 1 out of 64 is 0.016. What about the next number? For 1.33, it appears 3 times, 3 out of 64 is 0.047, and so forth. So on the top row, horizontally, you have the possible values of x bar and the corresponding probability. This means some of the x bar values are repeated more than once. 1 appears only once, 4 also appears once. But 1.33 appears 3, so 3 out of 64. Similarly, the mean of 3.67 also appears 3 times. Probability is 3 out of 64, which is 0.047. So basically, we have the probability of each sample means, or the relative frequency of each sample means. This is a probability distribution, okay, of x bar. In the tetrahedral exam, the population is 1, 2, 3, and 4. 4 sides, 1, 2, 3, and 4. Each is equally likely, so the probability of each is 1/4. It's a uniform distribution because each number appears 1 out of 4. Then you are drawing a sample of size 3. And notice what happens to the probability distribution of X bar. Now you have sample mean. On the second diagram, sample mean is on the horizontal axis. Probability on the vertical axis, you're approaching a bell-shaped diagram. The probability distribution histogram for the sampling distribution looks like the normal curve, whereas the probability histogram for the population does not. Remarkably, it is true that for any population, if the sample size is large enough, the sample mean X bar will be approximately normally distributed, means well-shaped. For a symmetric population like the one on the top, the sample mean is approximately normally distributed even for a small sample size like n equal to 3. So what are they doing here? They have the population probability density on the top. That is the probability and X values on the horizontal axis, number of repairs for the car. And notice it is skewed to the right. So it's positively skewed. Okay. Now they're taking samples of different sizes from that population probability on the top. First is sample size 3 on the left bottom. So you have X bar. Sample means on the horizontal axis, probability on the vertical axis. Bottom line, as you increase the sample size, you slowly approach the bell-shaped curve. Finally, when the sample size n is 30, the probability distribution of X bar, which is also called sampling distribution, is approximately bell-shaped. The size of the sample needed to obtain approximately normality depends mostly on the skewness of the population. In practice, a sample of size n greater than 30 is large enough. So that takes us to the central limit theorem, which states let X bar be the mean of a large means what? N greater than 30. Okay, so you have a sample of size greater than 30, greater equal to 30. Simple random sample from a population with a mean mu and standard deviation sigma. Then X bar has approximately normal distribution. Now we're talking about the sampling distribution. Its center where the peak is the highest, mu X bar is equal to the mean of the population. However, the standard deviation is thinner. It's population standard deviation divided by square root of n. The central limit theorem applies for all populations. However, for symmetric population, a smaller sample size may suffice. If the population itself is normal, the sample size X bar will be normal for any sample size. Okay, so I will do just a couple of them. A simple random sample of size 45, n greater than 30, drawn from a population. Notice the actual population, they did not say it is normal, but the sample size greater than 45. So that means the sampling distribution will be bell-shaped because the sample size is greater than 45. Okay. What about one on the extreme bottom right? Standard, they did not say what type of population, from just a population. Sample size is 24, less than 30. There is no guarantee that the sampling distribution or the probability distribution of X bar will be bell-shaped because the sample did not come from a normal population and the sample size is less than 30. Okay. Use central limit theorem to compute probabilities involving sample means. Okay. Recent data from US college indicates that the mean age of college student is 25 years with a standard deviation of 9.5 years. Simple random sample of 125 students is taken. What is the probability that the sample mean age of students is greater than X bar? Now we are talking the probability distribution of X bar or sampling distribution, and we want the probability that the sample mean is greater than 26. We have to be cautious. We have to change the standard deviation. The standard deviation of the sampling distribution will be 9.5 divided by second button and then x square gives me the square root. Inside the square root, our sample size is 125. So it is 0.8497 or 0.85. That's what we have to use. So now we do second verse number 2. We are on the right of 26. So lower boundary is 26. Upper boundary is 1, then second comma gives me the exponent 99. Mean is the mean of the population, which is 25. Standard deviation is now 0.85 or 0.849. And paste, enter, and enter. So that probability is 11.97. So there is a 11.97% chance that the sample mean age will be greater than 26. Okay. Now they want us to find the 30th percentile, same information. So the area to the left of the unknown x is 0.3, 30th percentile. So second verse 3 in norm, area is 0.3. What is the mean? Mean is equal to the mean of the population, which is 25. Standard deviation we have previously determined is 0.85. Okay. And I paste, enter, and enter. Is 24.55. So 30% of the students, college students, have a mean age less than 24.55. So this is on cattle whose mean is 1135 pounds, standard deviation is 97 pounds. This is the cattle weight. Now we are dealing with probability distribution of the sample mean weight of 100. So my sample size is 100, which is greater than 30. Okay. So the standard deviation of the sampling distribution will be 97 divided by square root of 100, which is 10, which is 9.7. So we want to find out the area to the left of 1100. So second verse, number 2, the lower boundary is a very large number on the left. So it is minus 1 E99. Upper is 1100. Mean is mean of the population, which is 1135 pounds. The standard deviation is 9.7, not 9.97. Standard deviation is 9.7. Paste, enter, and enter. And that's a very small number, 0.00015. So it would be unusual for the sample mean because it's less than 0.05. So it will be unusual for the sample mean to be less than 1100. Okay. Let's do number 2. Population has a mean of 47.5, standard deviation 12.6, and you are drawing a sample of size 1112. So sample standard deviation will be 12.6, or sampling standard deviation. Standard deviation of the sampling distribution will be 12.6, which is the population standard deviation divided by second x squared, which gives me the square root. Inside the square root, sample size is 112. So the standard deviation of the sampling distribution will be 1.19. So we want probability between 45 and 48. Remember, the standard deviation of the sampling distribution is 1.19. So second verse 2, between 45 and 48, lower is 45, upper is 48. Mean is same as mean of the population, which is 47.5. Standard deviation is 112.6 divided by square root of 112. So you can type that in the sigma also. It is 12.6 divided by second x squared gives me the square root. Inside the square root, 112, right parenthesis, and go down to paste and hit enter and enter. And that is 0.64448. Okay, 0.6449 they have written. Would it be unusual for x to be greater than 48? So what is the probability greater than 48? So second verse 2, lower boundary is 48, upper boundary on the right of 48 is 1, second comma gives me the E, 99, mean is 47.5, standard deviation is 12.6 divided by square root of 112, paste, enter and enter. That probability is greater than 0.05. So it is not unusual for the sample mean to be greater than 48. So that's why 2B answer is no, not unusual. Okay. That's it for today. I'll stop here today. If you have any question or comment, write me a note. If you like this video, please give me a thumbs up. I really appreciate that. That motivates me to produce more useful videos. If you like this video, share with your friends. You and your friends, please subscribe to my channel by hitting the red subscribe button on the bottom right corner. And please do not forget to watch me tomorrow when I'll be back with another interesting topic. Thanks for watching. Thanks for taking the time to watch my video. I appreciate that, and I will see you tomorrow. Take care. Have a nice day. See you next time.